the integral of 3x plus 26 divided by x squared minus x minus 6. And we have 5 options here. All of them seem to involve logs. And that's not too surprising. That happens frequently when we're dealing with this type of problem. Do we have an answer? E is a great answer. Good. Now, what kind of problem is this? And this is one of the things that you'll have to learn is to say, well, what tool do I use? So what kind of problem do we have? Now, in this case, we can spot we're dealing with something which has a fraction. The upstairs is a polynomial. The downstairs is a polynomial. And so we say, this is a rational function. Polynomial over polynomial. And once we see polynomial over polynomial, we tend to think, should we do partial fractions? And the goal of partial fractions is to say, let's pull things apart. So what we have at the start may be something that we can't do simply, but we could pull it apart into smaller pieces, and each piece is something that we could do. So this is the integral part, but the actual work is the algebra. So the goal is to say, well, we have 3x plus 26 over x squared minus x minus 6. We do a quick check of the degrees, and we see the upstairs has lower degree than the downstairs. We say, good. Don't have to do long divisions. We then factor the downstairs. And using the factoring, we say, well, we can pull it apart. It's going to be something over the first term plus something over the second term. When we say something, it's these unknowns, undetermined values. So the work is saying, well, what are these values? What are A and B? So we have to find A and B. And the easiest way that I know to find them, and people have all sorts of various tricks, but for me, it's get rid of fractions. Fractions are dangerous. So we multiply everything by this x minus 3 times x plus 2. So we end up with 3x plus 26 equals a times x plus 2 plus b times x minus 3. And from here, you have two polynomials are equal. There's lots of ways to go about this. I always like to say, make good choices. Make good choices. Choose values for x that make things simpler. What's a good choice? Make zeros. Zeros are a friend. So for instance, here, this x minus 3, to make that 0, you plug in 3. So you plug 3 into both sides because they have to be equal, and that leads you to the conclusion that a equals 7. And you say, well, this x plus 2, what makes that 0 is negative 2. So you plug in negative 2 into both sides, and that leads you to b equals negative 4, which tells us that 3x plus 26 over x squared minus x minus 6 can be written as 7 over x minus 3 minus 4 over x plus 2. So this was partial fractions, the algebra, which told us that we can rewrite our integral in that form. Now that we rewrote our integral, we're in the home stretch. Each one of these is a relatively simple, straightforward piece to integrate. So they're both logs, and then we use property of logs to put them together. All right, so that's partial fractions. What we would have done last time in class if there hadn't been a blizzard. That's all right. Hopefully there is a video, so I encourage you to watch that. Any questions? Okay, good. Well, I hope you're ready, because you will see partial fractions, as you will see everything, on the upcoming exams. All right. Our thought for the day, stand up to your obstacles and do something about them. You will find that they haven't half the strength you think they have, which is another way of saying it's not as bad as you think. Sometimes we think like, it's hopeless. It's not going to work. I won't even start. But if you can get yourself to start, you discover it's not so hopeless. Like learning how you integrate things. It can feel hopeless, but then you start and you practice. You start learning patterns. You start learning the tools. And you discover it's not half as bad as you think. It's not trivial, but you can do it. You can do it. Okay, so what are we doing today? Well, Our goal for today is we're reviewing and practicing what we should have learned this week: trig substitution and partial fractions. And they do connect together. So let me talk about why I like to have these things come together. So I've been alluding to this in various times, where there are good plus signs and there are bad plus signs. A good plus sign is something which helps us pull things apart or can help us push things together. So in other words, we can use linearity. So if I wanted to integrate x squared plus sine of x, I can say, well, I can think about it as the integral of x squared and the integral of sine x. That's an example of a good plus sign, very simple case. A bad plus sign is when we have have plus signs in inconvenient locations, such as a square root or such as a denominator. And so what can happen? Well, some people get tempted to say, I'll take the square root of x squared plus 4 by taking the square root of x squared plus the square root of 4. And notice, this indicates that's not good. Don't do it. Addition and powers do not mix. So you say, well, okay, if I can't do that, what can we do? And the answer is trig substitution. Trig substitution helps deal with plus signs showing up in square roots. Now, it's not the only way that we deal with plus signs and square roots, but it's a good way. Now, what's the other case? Well, we have a plus sign downstairs, and some people are tempted to say, 1 over x squared plus 3x plus 2, it's 1 over x squared plus 1 over 3x plus 1 over 2. And again, notice, this is indicating don't do that, because addition and division do not mix that way. You have to be careful. So then what's the right approach? Partial fractions. So I like to think of trig substitution partial fractions are giving us ways to deal with our challenging plus signs. All right, so let's do a quick reminder. This will look a little bit familiar because I just grabbed this slide. Okay, so this is our trig substitution procedure. Nothing new. But what's the process? Well, first thing is to identify and carry out the substitution. Now, the usual way we figure out, there's probably a trig substitution involved, is we see a square root with a plus sign in it. So when we see a square root with a plus sign, we're thinking, could this be approached with trig substitution? And we say, well, let's think about it. I need to be able to write it in one of 3 different ways, where I have a being a number, u being something with a variable. I will say on the equation sheet we did b instead of a, where b is a number, u is a variable thing. But that was mostly because a and u looked way too similar when we printed it out. So if I see number squared minus function squared, substitute in u equals a sine theta. Number squared plus function squared, u equals a tangent theta. Function squared minus number squared, u equals a secant theta. And this basic part right here you can figure out because it's on the formula sheet. So it's mostly a matter of let me make sure I have it in the right form. Keep in mind, you may have to complete the square. And so you may have to do a little bit of legwork, but not too much. But once you understand the substitution, you just say, look, make sure you count for all the terms in your substitution. It turns the problem into a trig integral, and we use trig integral techniques. So carry out that trig integral, and life is good. We're basically done, especially if it's a definite integral. If it's not, we have to undo the substitution, so you channel your inner SOHCAHTOA. And, it's like the song, SOHCAHTOA, where the wind goes. No, it's not that kind of song. But remember SOHCAHTOA. You'll need that. Because what will happen is you're going to make triangles. So you have to understand how triangles fit together. Sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. So for instance, if say I pick the tangent substitution, if u equals a tangent theta, well that says tangent theta is u over a. Draw the triangle, and the TOA says I should have opposite over adjacent. So I think opposite, adjacent, UA. And then Pythagorean theorem gives you your third side. And you might say, whoa, that's amazing. That looks really familiar. It has to happen. Otherwise, you did something wrong. And now I can start reading off trig functions. If I want the sine, well, that's opposite over hypotenuse, u over square root of a squared plus u squared. If I want cosine, adjacent over hypotenuse. If I want secant, hypotenuse over adjacent, so forth and so on. So be ready, if you have an indefinite integral, to carry out that part. All right, any questions on the procedure? Let's try it in practice then. A nice warm-up problem. Find the integral of x arc sine of x divided by 1 minus x squared to the 3/2 power dx. Okay. Well, probably not the integral you'd like to see, but it's the integral that we have. All right. Is there anything that tells us trig substitution, like something that says, aha, I see something, I'm thinking trig substitution? And not the arc sine of x part. What's something we look for when we think trig sub? If we want to do trig sub, what do we tend to look for? Do we have a square root? How do we know we have a square root? Yeah, see that over 2? That's secret code for it's a square root. So we say, oh, okay, so this is a square root. So we need to figure out what kind of substitution to make. So we're going to grab this inner part here, this 1 minus x squared. And what we'd like to do is we'd like to write it in the form of a squared minus u squared, a squared plus u squared, or u squared minus a squared. Which form is it in? Yeah, it's a squared minus u squared. So where a is 1 and u is x. So normally this tells us if I see a squared minus u squared, the substitution is u equals a sine theta. So for us, since u equals x, a equals 1, this says your substitution is x equals sine theta. All right, so that's our substitution we're going to be making. Well, we do a couple of extra notes here. If x equals sine theta, what's the derivative of x? Cosine. Derivative of sine is cosine. And we throw in the d theta, because we have to account for that dx. And then the other thing, of course, is to say, well, what happens to square root of 1 minus x squared? Well, that's square root 1 minus sine squared, which is square root of cosine squared, which is cosine. All right. So with that in place, we start updating. Everything has to be accounted for. So what will the x become? Yeah, sine theta. Okay. How about arc sine of x? What will that become? If x equals sine theta, what is arc sine of x? Theta. So I'll put the theta in front just to help. It's a little bit easier to parse. Theta, sine theta. Now, the downstairs, when we see this 1 minus x squared to the 3/2, that's really 1 minus x squared to the 1/2 cubed. That's what 1 minus x squared to the 3/2 means. So what does the downstairs become? Cosine cubed. And the dx is cosine. All right. Good. Good. Well, let's see, what can we say here? This is the integral of, there's a theta, and we can cancel a single cosine. So we have sine theta over cosine squared theta d theta. All right. Progress. Progress. So, what can we do here? Oh, we could do that. Okay. So notice you could rewrite sine over cosine squared in terms of secants and tangents. Okay, so we have a theta. And if you take a 1 over cosine, that's a single secant. And a sine over cosine, that's a tangent. All right, so we have theta times secant times tangent. All right, so we have to integrate that. What do we do? Do we have ways to integrate this? By parts! Ha-ha! Yes! You have to be open to saying, hey, I may start a problem in one setting, and I may have to shift and use a different tool partway through. So we're going to go by parts. Part by part. What's the part you want to integrate? What's the part you want to differentiate? Okay, secant tangent seems pretty reasonable for something to integrate because it's actually, the reason we think it's pretty straightforward is we know something where the derivative is secant tangent. So in other words, secant tangent has a nice antiderivative. And the theta is a good choice for you because if we take the derivative of that, what happens? It becomes 1. All right, so what is the antiderivative of secant tangent? Secant. So we have uv, theta, secant theta, minus the integral v du, secant theta d theta. All right, well, that seems more straightforward. Do we know the integral of secant? Yes. What is it? Natural log of secant theta plus tangent theta. And when in doubt, we can get that from the formula sheet, tack on a plus c. Ah, success. Or, as the Klingons would say, kapla, which of course is Klingon for success. All right, we did it. Are we done? No. Oh, not very enthusiastic with that. No, we're not done. It never ends. Okay, what needs to be done? What's the last thing we need to do? Go back to x. Okay, so we'll make some notes over here. We knew that x equals sine theta. One thing that tells us is that theta is arc sine of x, which we used when we did the original substitution. So that'll help take care of that. But we also say, hey, since I need a ratio, I like to think of my trig functions as ratio. I can think of sine of theta as x over 1. And draw a triangle. Put theta in the corner. And we think, okay, sine is opposite over hypotenuse. Opposite over hypotenuse. X over 1. Pythagorean theorem will give us our missing side. Square root of 1 minus x squared. All right, so we go through term by term. Theta, we already said, that's arc sine of x. Secant of theta, what would that be? So come to the triangle. Which sides do you take the ratio of? So it's the adjacent side and the hypotenuse side. Which one's on the top, which one's on the bottom? Well, so adjacent over hypotenuse is cosine. Hypotenuse over adjacent is secant. So it'll be 1 over square root of 1 minus x squared. So that's that term. Minus log secant hypotenuse over adjacent, 1 over square root of 1 minus x squared. What is tangent? Opposite over adjacent. X over square root of 1 minus x squared. And there we go. So it's something we can do. We have the technology. Nice. Nice. Now, in case you're wondering, this is harder than what you'd see on the exam. But it's good to do hard problems. You work on the hard problems. All right, any questions? We're good? You're masters of trig substitution? All right. Well, since we're great at trig substitution, we can switch and talk partial fractions. Okay, so what is partial fractions? We have polynomial over polynomial, and there's a couple of steps. There's a step I call step 0. I call it 0 not because I'm trying to channel my inner computer scientist, but I call it step 0 because it's so often not done. Well, you have to check, and that is, do you need to do long division? The theory of partial fractions is about pooling rational functions into parts. The process requires that the numerator has lower degree than the denominator. So if you throw in a partial fractions problem without doing your long division, if it's needed, you'll get the wrong answer. How do you do long division? Work with leading terms. All right, so that's step 0. Okay, so now we say we have a rational function. Things are in nice form. Lower degree upstairs than downstairs. So the real first step, factor the denominator. Now, that's an easy thing to say. Mathematicians know that there's a beautiful theory that says, yes, you can always do it. And it's fundamental. It's called the fundamental theorem of algebra. Mathematicians also know that in practice, you will have a very hard time once you start getting up to like cubics and quartics. And quintics are just hopeless. So here's the good news. It's going to be something easy to factor, or it will be factored for you. So don't panic about the factoring part. If you do have to factor, just know it'll be something straightforward. Now, how do we factor it? There's linear terms and there's irreducible quadratic terms. So those are the two types of things we might encounter. The reason we have irreducible quadratic is we may have situations like x squared plus 1. And you say, well, hey, you could factor x squared plus 1 a little bit further. It turns out it's x plus I times x minus I. But now, all of a sudden, you have i's in there, and that just feels too complex. And so we don't like that. So we stop at irreducible quadratics so that everything, we want to keep it real. Keeping it real, that's our goal. Okay, so once we factored, again, usually given to us are very quick. This is the important step, is we can say, we know we can pull it apart. We need to understand what it's going to look like. So we look at the factorization, and if I see a term like x minus a to some power, that says, well, I'm going to have things that look like x minus a, and I'm going to work my way up to the power. So if I see just a single x minus a, that's all I'll have. If I see an x minus a squared, then I'm going to work my way up to x minus a squared. Now, in theory, of course, we can go further. In practice, we don't. If I see irreducible quadratic, then again, same process. I work my way up. Because this is quadratic downstairs, and I'm not looking at this part, I'm looking at what's on the inside, I have to have the upstairs be a little bit different. So now, instead of just a constant, it's a constant x plus a constant. Okay, so for everything in your factorization of your denominator, don't bother factoring the numerator. That's useless, won't get you anything. It's just the denominator. Figure out the right form. And here's a tip to check. How many constants should you have? I don't think I've written it down on this page, but I've said it. How many constants should you have? What?
Power downstairs.
The power downstairs, yeah, the degree of the denominator. If you have fewer constants than the degree of the denominator, you've lost some constants. If you have more constants in the degree of the denominator, you've added constants you didn't need. You should have exactly whatever the highest power is downstairs, the degree of the downstairs. All right, so once you figure out the right form, then the last step is you solve for the unknown coefficients, clear your denominators, and I like to say, make good choices. Make good choices as much as possible. So in other words, plug in values for x, and that helps zero out a lot of terms. That can get you some constants very quickly. If that doesn't work, then you expand both sides and you compare coefficients. All right, so that's the process. Any questions on the process? Okay, well, let's try a problem. I think this comes from an old exam. All right, find the integral of 3 natural log of x plus 3 over x squared dx. Now, before we start, is this a problem that we can use partial fractions on? And why not? Okay, so there's 2 questions. Is this a problem we can use partial fractions on? No. At least not right now. Why can't we use partial fractions here? Log is not a polynomial. You have to have polynomial over polynomial. If you don't have polynomial over polynomial, it's not partial fractions, so don't do it. Okay, well, great. So what can we do? Well, that's certainly one approach. We can meditate and think. What?
By parts.
By parts? Brilliant. Great idea. What's a suggestion that we have a by parts type integral? Other than we have a voice whispering in our head, by parts, by parts. We have this part, log of x plus 3. Log is something we don't want to integrate, but what's true about log? Integral is terrible, but derivative is nice. If you have a piece of your integral where you say, oh, this is terrible to integrate. Oh, but wait a second, its derivative is nice. Then one of 2 things is true. Either there's a substitution or it's like a by parts. Substitution wouldn't make a lot of sense here because I would need a 1 over x plus 3 to help. So by parts sounds like the right idea. So let's think of this in the following way. We're going to think of this as log of x plus 3 and 3 over x squared. So this first part, we don't want to integrate, so that's the part we differentiate. And then the rest of it will be the part we integrate. Derivative of log of x plus 3. We said it was easy to differentiate, so hopefully that's still true. 1 over x plus 3, yes! And we throw in the dx for good measure. Antiderivative of 3 over x squared, which is, by the way, the same as 3x to the negative 2 power. Yeah, so it'll be negative 3 over x. Or if you like, it's negative 3x to the minus 1 power. So you add 1 to the power of negative 2, divide by that new power. Okay, so according to partial fractions, we have uv, so minus 3 over x, log x plus 3, subtract the integral of v du. Well, minus, there's another minus, so this will end up becoming a plus in a second here. But when I multiply these together, we really have a 3 over x times x plus 3. And again, because there's a minus, I'm going to go ahead and put that out front. All right. So that's one round of integration by parts. So now what do we do? This part's done. We don't have to do anything with the minus 3 over x log x plus 3. We like that. We now have to think about this piece. 3 over x times x plus 3. What can we do there? Partial fractions. Yes! Ha ha ha! So it didn't look like a partial fractions at the start, but when we used a good technique, it became partial fractions. Woohoo! Okay, so we'll do some partial fractions work. Now, let's talk our way through the process. Do we have the degree upstairs less than the degree downstairs? Yes. Is the downstairs already factored for us?
No. Yes.
Yes. Yes, I like that. No, yes. It was very quick. Woo. So it's already factored x and x plus 3. So we jump right into the fun part. So we have 3 over x times x plus 3. We say, okay, we look at our pieces downstairs. Well, we have an x term, which means that we're going to have something over x, and that something is we don't know. So we put an a. And then we say, okay, but what else do we have? Well, we have an x plus 3 term. So we're going to have something over x plus 3. What is that something? We don't know. That's our goal. So we sit down and say, what's the right way to pull it apart? Okay, the next step. Well, ultimately the next step is solve for a and b. To help us solve for a and b, what comes next? Get rid of fractions. Oh, fractions are dangerous. They often lead to mistakes, so we get rid of them so that we will have fewer mistakes. So we're going to multiply by the original denominator, and we do that on both sides. And when we do that, we come to the conclusion the left side becomes 3. When we multiply this a over x, x times x plus 3, that leaves us with a times x plus 3. Here, the b over x plus 3 times x over times x plus 3. The x plus 3's cancel, so we get b times x. Now we just need to solve for a and b. I don't want to make it sound like there's some work involved, but that's what we need to do. All right. So we can expand and compare coefficients, or we can make good choices. Both methods can help. Which one do you want to do? Yeah, I strongly encourage you to make good choices. If you need to expand, you do it. But if you can make good choices, that's good. So what's a good choice? 0 is a great choice. Because when we plug in x equals 0, the second term goes away. So you get 3 equals 3 times a. Or a equals 1. What's another good choice? -3. Great choice because minus 3 plus 3 is 0. So that's going to make the first term go away. So we get 3. Notice it doesn't matter what you plug in. It's always 3 on the left-hand side. But if we had more stuff, it would be a little bit more complicated. And so 3 equals minus 3 times b, or b equals -1. So the partial fractions work on the side says 3 over x times x plus 3 is equal to a, 1 over x, and b, minus 1 over x plus 3. I have seen many people who have done great work, and they would get this correct, but then they would put the wrong numbers in the wrong places. So make sure that once you've done all the work, you're putting the right numbers in the right places. So whatever a is goes in the right place, whatever b is goes in the right place. Okay, so that was sort of an algebra intermission. But now what that allows us to do is say this second integral, I can replace what we're integrating by something equivalent, namely 1 over x minus 1 over x plus 3. All right, so we're in the home stretch. What's the integral of 1 over x? Natural log of x. You see it a lot when you're dealing with rational functions. What's the derivative of 1 over x plus 3? ln of x plus 3. And there we go. Woohoo! Wait, what? No? Ah, plus c. Okay, good. Whew. There was enough space. All right. So See, that's not too bad. We can do these problems, which is good, because we might have to do these problems. All right, I think we have time for at least one more problem. What kind of problem do you want to see? Partial fractions or trig substitution? Trig sub? We can try that. All right. The region bounded by y equals x over 4 plus x squared to the 5 halves, the x-axis, and x equals 2, is rotated around the y-axis. Find the volume of the solid. And so we have something. Here's x equals 2. So here's our region, and we're spinning around the y-axis. All right. So this is good. This is like we're doing an application here. This comes from an old final. Good times we're having. So that means that this shouldn't be too bad. Okay, so channeling our inner, setting things up, because that's still part of this portion of the class, setting things up. Are we going to want to slice vertically or horizontally? And why is the answer vertically? So are we going to want to slice vertically or horizontally? Vertically, good. And why do we want to slice vertically? Yeah, because we're already in terms of x. It's going to be hopeless to solve for y. And so we don't want to be hopeless. We want to have hope. So think about what that slice is going to do when you spin it around. What are you forming here? What's your shape? It's a shell or a cylinder. So this is aha. We're going to be doing shell method. Okay, so we look up on our little sheet. Shell method says integrate a to b, 2 pi. There's a radius. There's a height. And there's a width, our thickness. Okay, so for us, we start going through and writing things down. Our region, where are we going between? 0 and 2. 2 pi is 2 pi. Radius is how far you are to where you spin. How far are we from where we spin? X. Our height is our height, which is the function. X over 4 plus x squared to the 5 halves. And our width is this little tiny piece here, dx. So that's our integral. Okay, cool. And now we're ready. What tells us, what technique are we using here? We're using trig sub. What's the clue that it's trig sub? Yeah, there's this square root here. So 4 plus x squared, that looks like 2 squared plus x squared. So where we have a squared plus u squared. So a is 2 and u is x. A squared plus u squared, what kind of substitution are we making? Tangent. All right. So u, I could have written this. U equals a tangent theta. In this case, x equals 2 tangent theta. So now we make some notes. The square root of 4 plus x squared is the square root of 4 plus 4 tangent squared. Well, that's really the square root of 4 times 1 plus tangent squared. 1 plus tangent squared has another name, secant squared. And we say, aha, so that really is 2 secant. So, all right, there's a lot of secants downstairs, is what we're going to see. What's the derivative of 2 tangent theta? 2 secant squared. Okay, I think we have everything we need. So let's see where we are. We are integral 0 to 2 pi. We have x squared, which will become 2 tangent theta squared. So those are the x's, x squared. The downstairs, what are we going to have there? And I lied to you, this is not 0 to 2 anymore. I'll fix that. The downstairs, 4 plus x squared to the 5/2 becomes 2 secant theta to the 5th. The dx, 2 secant squared theta d theta. All right, I did the bounds wrong. The bounds are not 0 to 2 because the 0 to 2 are x bounds. X equals 0 to x equals 2. We got to update it to theta bounds. So we plug in to get our new bounds. New bounds. We'll do it down here. So when we plug in x equals 0, 0 equals 2 tangent theta. What's an angle that gives us that? 0. So see, our bound wasn't 0, it's actually 0. Okay, good. Glad we caught that. Well, the other one will be more interesting. We plug in 2. So plug in x equals 2. 2 equals 2 tangent theta. Or if you like, tangent theta equals 1. Okay, all right. I'll buy that. What's an angle that does that? Pi over 4. Okay, so that says our upper bound is pi over 4. All right, so we've got a lot of 2's here. Let's see if we can count our 2's. How many do we have? We have 1, 2, 3, 4 upstairs, and 5 downstairs. If we put all our 2's together, how much are we left with? We're left with a single 2, and it's going to be downstairs. So there's 1, 2, 3, 4 upstairs, 1, 2, 3, 4, 5 downstairs, so that means 1 downstairs. So pi over 2, integral 0 to pi over 4. We have a tangent squared upstairs, and then we have secant squared, secant to the 5th. That leaves us with a secant cubed downstairs. Okay, so now we just have to figure out how to integrate tangent squared over secant cubed. How bad could that be? How bad could that be? Well, when in doubt, I'm feeling some doubt, go back to sines and cosines. What's another way to say tangent squared? Sine squared over cosine squared. Now, what's another way to say secant cubed? 1 over cosine cubed. But since it's downstairs, I can flip it. The secant cubed will become, when we flip it, cosine cubed over 1. Do you see anything convenient? This is the same as pi halves, integral 0 to pi over 4 of sine squared theta cosine theta d theta. All right. That seems more reasonable than tangent squared over secant cubed. At least it seems more reasonable. Now what can we do? We can do another u sub. And you're like, what? Wait, we already did a sub. Are we allowed to do a double sub? Yes, you can do whatever you want. It's your integral. Enjoy the ride. It's okay to make multiple substitutions. Let u equals sine theta. Du, cosine theta d theta. So we still have our pi over 2. We have an integral u squared du. But what's our bound? We should be careful with our bounds. When we plug in 0, It's no longer 0, it's now 0. When we plug in pi over 4, it becomes root 2 over 2. Okay, so we're almost done. Because this looks like an integral we can do. Integral of u to the squared, u to the power 2, well, it's going to be u to the power 3 divided by 3, giving us pi over 6 u cubed. Evaluate from 0 to root 2 over 2. Well, plug in 0, you get 0. So you get pi over 6 times, well, it's root 2 over 2, root 2 over 2, root 2 over 2. I'm just doing this to make some notes here. We can do a couple things. If I put 2 of these root 2's together, that cancels with a single 2. So our final answer, since there's lots of space up here, is pi square root of 2. 6 times 2 times 2 makes 24.